Hello, welcome again. We are solving some questions of heat transfer. The topic is one dimensional heat conduction. Question number 16 is a hot fluid is being conveyed through a long pipe of 4 centimeter outer diameter and covered with 2 centimeter thick insulation. It is proposed to reduce the conduction heat loss to the surrounding to one third of present rate by further covering with same insulation. The additional thickness of insulation is option A 5 centimeter, option B 10 centimeter, option C 12 centimeter, and option D 8 centimeter. So let R1 be the radius of the outer radius of the pipe or inner radius of the insulation. This is the R1, and R2 be the outer radius of the insulation without assuming additional thickness. Okay, so this is the insulation that is initially added, and so that the radius of outer radius becomes R2. Okay, and when suppose X the thickness of the insulation is further added to reduce heat transfer, then R3 be the radius, then and R3 will be R2 plus X. Okay, and K is conductivity of the insulation. Now from this R1 to R3 there is insulation of conductivity K, and from R1 to R2 is also conductivity is K. Same insulation from R1 to R3. Okay, so now if we take the first case, R1 and R2, then the heat loss by the existing installation is 2 pi K L T1 minus T2. T1 is temperature here inside the outer wall of the pipe, and T2 is your atmospheric temperature when this thickness is not been added. So the heat transfer is post Q1, that is 2 pi KL T1 minus T2 log E R2 by R1, because it is cylindrical coordinate, so resistance is ln R1 R2 by R1 divided by 2 pi KL. Okay, so when additional thickness has been added, so suppose Q2 be the heat transfer, and now we will take R3 in place of R2, and R3 is R2 plus X. So Q2 is just 2 pi KL T1 minus T2 divided by log E R2 plus X divided by R1. Okay, so X is additional thickness of insulation. Okay, so Q2 is equal to Q1 by 3, that is given. Okay, so Q2 is equal to Q1 by 3, that is given. Okay, and Q2 is your 2 pi KL T1 minus T2 divided by divided by log E R2 plus X divided by R1. Okay, and this is your Q1 is your 2 pi KL T1 minus T2 divided by log E R2 by R1, and this is 1 by 3, so it will be 1 by 3. So now this quantity will cancel out, so R2 plus X by R1, and if we can take this 3 here, R2 by R1 cube, so it will be R2 by plus X divided by R1 is equal to R2 by R1 cube. Okay, so R2 plus X divided by R1 will be R2 by R1, that is 4 by 2. R2 is your R2 is your 4, and R1 is your 2. Okay, so this will be your 4 by 2 or b to 2. So R2 plus X divided by R1 is equal to 8. So R2 plus X is equal to 8 R1, and X will be your 8 into 2 minus because R1 is 2 and R2 is 4, so X will be your 12 centimeter. So answer is additional thickness that is added to reduce the heat transfer by the factor of 1 by 3. So will be your 12 centimeter. So answer is option C. Okay. So answer is option. Next, question number 17. A steel pipe of 20 inner diameter and 2 thickness is covered with a 20 thick of fiberglass insulation. K is equal to 0.05 watt per meter per degree Kelvin. If the inside and outside conductive coefficient are 10 watt per meter square per degree and 5 watt per meter square per degree, the overall heat transfer coefficient based on inside diameter of the pipe, option A 2.789 watt per meter square per degree Kelvin per degree, and option B 3.129 watt per meter square per degree, option C 2.112 watt per meter square per degree, and option D 3.512 watt per meter square per degree. So this is the data are that R1 is 10 mm. So R1 is inner diameter of the pipe is 10 mm, and thickness and this R2 is 10 plus 2 outer diameter of inner radius is 10 mm, outer radius of pipe is 12 mm, and is an insulation of 20 mm is there. So R3 will be your 12 plus 32 12 plus 20 32 mm. Okay. So the thermal resistance to flow of heat are offered. These are the thermal resistance, and thermal resistance is inside for the as there is inside there is a liquid film, so its thermal resistance will be 1 by Hi Ai, so that will be 1 by Hi 2 pi Ri L. And for the pipe material, RT2, for the pipe material it is log E R2 by R1 divided by 2 pi K2L. So this is your pipe material, and K2 is the conductivity of the pipe material. And for insulation, for this insulation, the resistance is log E R3 by R2 2 pi K2L. And for the outside film, the resistance is 1 by H0 A0 1 by or the outer area 2 pi R3L. Okay. Now the temperature difference between this and this is Ti minus T0. So as 2 pi L is common in all the distances, so we can take that 2 pi L Ti minus T0 divided by these summation of these resistance. Okay. We can assume that the conductivity of steel pipe is very high as compared to the insulation, so we can neglect this part. Okay. So because steel pipe conductivity is very high and it is not given in the question also, so we can neglect this part. So the heat transfer will be 2 pi L Ti minus T0 divided by 1 by Hi Ri 1 by K2 L log E R3 by R2 plus 1 by H0 R3. Okay. And if we assume we want to find out the convective heat transfer coefficient, overall heat transfer coefficient based on inner area, then the heat transfer will be Ui Ai Ti minus T. Okay, and Ui Ai is 2 pi RL L. Okay, so equating these two, this and this, equating these two, we can get Ui. Okay, or we can cancel out this, and 1 by Ui Ri will be this. Okay, so now putting the values, we can find out Ui. So Ui comes out as 2.789 watt per meter square per degree. Okay, we have all the values, and we can put these values, okay, and find out Ui. So answer is option A.